Welcome back to another video with us here at LMDN STEM Academy. In this video, we will be working through the June 2012 Unit 1 Paper 2, and we'll be doing question 5, which centered around chemical equilibria. So this question says that we were supposed to copy and complete the table below to show the type of equilibrium for the selected equilibrium systems. So we have three systems here. And the first system is a system where there's saturated solution of a salt at room temperature. And then system 2 is a vertical balancing of a ruler on a flat surface. And then system 3 was the heating of limestone at 800 degrees Celsius. Okay? And so our answers here then would be that system 1 is a system where we have dynamic equilibrium taking place. It's a chemical reaction, in fact, with a saturated solution where you have particles, continuously going back and forth from being in their solid state to their ionized state. So it's an equilibrium that's there, dynamic equilibrium that's set up. And in this case, you have vertical balancing of a ruler on a flat surface. So that when the ruler is balanced, it's just completely static. It's at a standstill. There's nothing going on microscopically. It's just at a standstill. So that's a static equilibrium. And then heating of a limestone at 800 Celsius. Again, this is a chemical reaction, a chemical process. And that's a dynamic equilibrium that gets set up there because there are things happening at a microscopic level. Even if on the surface, macroscopically, it doesn't look like anything is happening, okay? So these two are dynamic and this one is static. All right, so let's move on to part 2 of that. So it says, state the two characteristics of the equilibrium represented by system 1 in the table above. So remember now, in system 1, what did we have again? We have that saturated solution of a salt at room temperature, which is the same as around 298 Kelvin, right? And so that kind of describes this equilibrium constant that we know that's known as KSP, right? So they're describing a KSP situation here. So we have a dynamic equilibrium, and really the features of, any dynamic equilibrium situation is that at equilibrium, the rate of the forward reaction is going to equal to the rate of the backward reaction. And then a second characteristic is that at equilibrium, right, when you have a dynamic system, the concentration of reactants and products are constant, right? Because you're constantly shuttling back and forth, right? And so that way, the concentration of the reactants and the products are actually going to be constant when you're at equilibrium, okay? So moving right along to 5B, 5B says that substance A, B, X, and Y form an equilibrium mixture represented by the equation below. And so they're showing us the equation below. We have A moles of A combining with B moles of B. Equilibration takes place, and you have X moles of X plus Y moles of Y. So we're being asked now to write the expression for the equilibrium constant, okay? So I write a Kc expression here, equilibrium constant in terms of concentrations. And so I'm going to write my products raised to their stoichiometric coefficient on the top, right? So I write X raised to X times Y raised to little y, and that's my top. And then in the bottom, in the denominator, I'm going to have my reactants raised to their respective powers or their respective stoichiometric coefficient. So that would be concentration of A raised to A, concentration of B raised to B, and together, that's the expression for my equilibrium constant. So moving right along, what deduction can be made when the equilibrium constant is much greater than 1? So we're saying if Kc, if this equilibrium constant is greater than 1, what does that mean, right? So from a mathematical standpoint, it would mean that we have more of our products, right? We'd have more of what's in the top. And that would make the Kc be much, much greater than 1. Okay? So remember now, if the top is big, then Kc will be big. Okay, and we're considering being greater than 1 a big, fairly, right, reasonably large number. And so what's happening is that the top is then favored. So we have mostly products at that equilibrium, okay, in that particular equilibrium. And so when the equilibrium constant is greater than 1, this means that the position of the equilibrium lies to the right, and we will mostly have products being present at equilibrium. So we have mostly species in the top. That makes Kc greater than 1. Okay. So part C says when solid bismuth 3 chloride, which is BiCl3, is added to water, a white precipitate of BiOCl is produced. These compounds form an equilibrium mixture represented by the equation shown here. So we have our bismuth 3 chloride aqueous plus water in the liquid form being equilibrium with the BiOCl solid plus 2 moles of HCl aqueous. So the first question wants us to explain why the white precipitate, which is BiOCl, so this guy, why does it disappear on the addition of aqueous HCl to the equilibrium mixture, right? So remember, at equilibrium, what we're saying is that we will see a white precipitate that's coming from the BiOCl being present, right? So let's populate our explanation here. The white precipitate seen at equilibrium is due to the presence of BiOCl. When HCl is added to the equilibrium mixture, we essentially increase the concentration of HCl. So I'm increasing this, I'm sending that up, right? I'm increasing that. In order to then use up that excess of HCl that I just dumped here, my reaction has to shift to the left, right? It has to shift over here. And that shift also results in us using up some of the BiOCl. So it's going to go back that way as well, the BiOCl. And so that will result in a disappearance of the white precipitate, because the white precipitate is only there when we are having BiOCl in that equilibrium mixture. So if I shift the equilibrium position to the left, I am resulting in that white precipitate. It will result in the white precipitate disappearing. Okay, so that's how we explain that phenomenon. Okay, so here's our next part. So here's part 2 of this. Part 2 says, explain what would be observed if a large volume of water was added to the equilibrium mixture, right? So I have my equilibrium mixture. Everything is like happy and nice at equilibrium, and I dump in a bunch of water into that. So here's what's going to happen now. Since water is a solvent, if a large volume of water is added to the equilibrium mixture, we would essentially be decreasing the concentration of all reactants and products. So we're diluting everything, essentially, right? So we're lowering the concentration of everything. So the way that the system is going to account for that change, is that the position of the equilibrium will have to shift to the right where there are more moles or more molecules, right? You see that on the left, there are 2 moles of molecules. So when you add them together, 1 mole of this and 1 mole of that, you get 2. And on the right, you have 1 mole of this and 2 moles of this. So you'd have 3 moles total on the right. So let me just jot that down. That on the right-hand side, you have 3 moles of stuff in all. And on the left-hand side, you have 2 moles of stuff. So if I add a bunch of water, dilute everything, brought the concentration of everything way down, then the system has to compensate for that drop somehow. And the way that it does that is by shifting to the side where there are more molecules. So there will be a higher concentration over this side on the sheer basis of there being more molecules present on that side. Okay? And so as a result of the position of the equilibrium, the position of the equilibrium will shift to the right, where there are more molecules or moles, in order to increase the concentration of the equilibrium mixture again. Okay? So if you drop it, it has to find a way to come back up. And that's what the water did. And so it had to find a way to come back up. So it shifted to the right, where there were more moles. Okay? It's a similar thing as to what would happen if you were to decrease the pressure. You would have to find the side where there are more molecules. So this dilution by water is analogous to what would happen in the case of a pressure drop. Okay? So just keep that in mind as you're explaining this effect of dilution. Okay? So let's move on to part D. So part D says phosphorus 5 chloride, which is PCl5, decomposes at 250 degrees Celsius and forms an equilibrium mixture represented by the equation, which shows PCl5 gas being decomposed into PCl3 gas and Cl2 gas. Okay? One equilibrium mixture at this temperature contains PCl5 and PCl3 at concentrations of 0.2 mole per dm cube and 0.01 mole per dm cube, respectively. So given that the Kc at this 250 degrees C is 0.1 mole per dm cube, we're being asked to calculate the concentration of Cl2 in the mixture. Okay? So first, in order to do this, we're going to have to write our equilibrium expression. We're going to have to write our Kc for this equilibrium first and foremost. So we write our Kc, we're going to write our products, okay, concentration of our products over the concentration of our reactant, and set that equal to 0.19 mole per dm cube because that's the value of our Kc, okay? And so what we need to do is, because we want to find the concentration of Cl2, we're going to have to rearrange this whole thing, making Cl2 the subject. Okay, so that's what I did down here. I rearranged the Kc expression to make Cl2 concentration the subject. And when I did that, all I ended up with was this expression where Kc times the concentration of PCl5 would be divided by the concentration of PCl3. And remember, these are our equilibrium concentrations because the Kc is an equilibrium expression in terms of equilibrium concentrations. And so the value that I'm plugging in here and here are these numbers here, the 0.20 and the 0.010. So I come over here, put my Kc here, and I multiply that by the PCl5, which is 0.20. So that's that here. And then I'm going to divide that whole thing by the concentration of PCl3, which is this. Okay? And so when I plug in all the numbers and bring through all the math, and I'm keeping track of my units as well, I end up with a concentration of Cl2 being 3.8 mole per dm cube. Okay? So that's our answer. So all we had to do for this was write our Kc expression, then rearrange to find concentration of Cl2, and then plug in, and here we are. Okay, so with that, we've come to the end of this question. Definitely give this video a like, definitely subscribe to this channel, share it with your classmates, and we'll see you in our next video.